Welcome to Math with Michelle, where math finally makes sense. Whether you're tackling high school math or diving into college algebra, I'm here to break it down step by step with real examples and zero stress. From algebra to functions, graphs to equations, I've got it covered. Hit that like button and let's master math together.
Welcome to Properties of Logarithms. I really want to do in this video a deep explanation of why the rules are what the rules are so that you can understand instead of it just being, hey, because someone told you to. So 3 squared we know is 9. And if you've seen my other videos, I'm just going to reformat into the log form. Therefore 2 would be log base 3 of 9. We know that 3 to the third power is 27. So therefore 3 would equal log base 3 of 27, just from our formatting rules from previous videos. And we also know 3 to the fifth is 243. So therefore when I isolate my exponent, because that's what logs do, they isolate your exponent, is log base 5 243. Okay, that's all fine and great, but why am I going through all that? Well, I believe you know the following statement. And I think you'll agree with this. 2 plus 3 is 5. Fair assessment? So by substituting 2, it was in purple, right? 2, an equivalent statement for 2 would be log base 3 of 9. Plus, probably see where I'm going with this with the color coding. The brown 3 would equal log base 3 of 27. And then we have the blue. Log, and I wrote the wrong number there, base 3 of 243. Now it's important to note this is all log base 3 in all single one of these, so that's very important. But what do you notice about what's on the left versus what's on the right? So a couple of things I notice. I know that x squared times x cubed equals x to the fifth. Because when I multiply bases, I add my exponents. Wait, I add my exponents? And don't logs equal exponents? So in this case, 3 squared times 3 cubed equals 3 to the fifth, right? And that's with multiplying. Well, check out what happens when you multiply 9 times 27. You do indeed get 243. And it's this relationship between when you add exponents, you multiply your bases, that gives us that relationship so that we can conclude what's known as the product rule. Log base A of x plus log base A, same base, of y equals log base A of xy. And I have worked with problems where it was more efficient to have it in the product versus where it was more efficient to have it in the expanded form. Now, I could do the same kind of thing here with quotients, or with the quotient rule. Okay? So we know that 5 minus 3 equals 2. So that would give us log base 3 of 243 minus log base 3 of 27 equals log base 3 of 9. So now, before we had to do 9 times 27 to get 243. Now it's 243 divided by 27 gives you 9. So our quotient rule is very similar. Log base A of something minus log base A of something else equals, instead of multiplying, we divide. And that's because when you divide bases, you subtract your exponents. So that's the product rule and the quotient rule. So now we're going to develop the power rule. And I'm going to do this with common log. Okay. So we know log of x to the fourth is log of x times x times x times x. But the product rule says I can expand it out to where I only have, instead of going from a product, I can expand it to a sum. So log of x plus log of x plus log of x plus log of x. That's a lot to write, but aren't they like terms? So we can just add our coefficients. And when we add our coefficients, we get 4 log x's. Anyone see a shortcut from the beginning to the end? If you do, that's your power rule. Your power rule states, and I'm using random letters. Every book uses different letters. The letters are just placeholders. So even though I keep calling it base A, they could have called it base M. Log of h to the x, I'm being weird with my letters, will be equal to x times log base A of h. Now, if they don't put parentheses around it, there's assumed parentheses, kind of like there's assumed parentheses under a radical sign. So our power rule just allows us to move our power out front. Now, we can go from the left side to the right side or the right side to the left side. It depends on what we need in the moment. So we're just going to expand and work on things first. And I'm going to add a word completely. Log base 7 of 12x cubed divided by yz squared. Okay, and I'm going to do this a couple ways so that you understand what's going on here. I'm going to remind you that 12 is 2 squared times 3. We have multiplying by x cubed. And we could rewrite this to where it's times y to the negative 1 times z to the negative second. And I'm actually going to do it this way for this problem. So I've written it as a prime factorization with only a numerator. Okay? So when I'm expanding, I'm trying to rewrite it to where only one thing is inside the parenthesis. So I will have log base 7 of 2 squared, multiply, so plus log base 7 of the next factor, and there's a times sign, so plus log base 7 of the next factor, plus log base 7 of the next factor, plus log base 7 of the next factor. Whew, that was a lot. However, we also don't like exponents when we expand completely, so now we're going to move those powers in front using the power rule. 2 log 7 of 2 plus log 7 of 3 plus 3 log 7 of x. Now notice that we're going to put a negative 1 in front. So instead of writing plus negative 1, I'm going to write minus 1. And the same thing here, instead of plus negative 2, I'm going to write minus 2. Okay, so that quotient rule actually ended up coming out, and it saved us from making a sign error. So if you'll notice, y and z squared were both in the denominator, so they divided by y, they also divided by z squared. Because those were both in the denominator, they both wound up being a minus because they're technically part of that quotient property. So if you don't like using the quotient property, can you rewrite it like this first and then just use the product and the power property? Absolutely. And the good news is 2 is a prime number, 3 is a prime number, x is prime, y is prime, and z is prime. So there's only a single thing inside of each. Before I go on any further, I want to note a couple things. If I have log base 3 of 3, or log base 5 of 5, or natural log of e, or common log of 10. Remember, natural log of e is really log base e of e. Common log is really log base 10 of 10. So you'll notice that the base and the number match every single time, right? And this is a power of 1, a power of 1, a power of 1, a power of 1, right? On all of them. Well, 3 to what power is 3? 5 to what power is 5? E to what power is E? 10 to what power is 10? So that kind of is just a basic rule we can note, is that anytime our base and what's inside match, they basically cancel out and leave us with 1. So what if I had log base x of x cubed? Well, I can't just make it cancel out and make it 1, because that's not true. But what I can do is I can move the power out front using that power property. And then I can say it's 3 times 1. So just remember that that's something that we might keep in mind when these numbers match, because basically they're inverses of each other. They cancel each other out. Okay, so what if I were to expand natural log of x cubed times y squared? Just make this one a little bit simpler. Well, you might go, well, you didn't say anything about natural log rules, but isn't natural log a log? Yeah, it's just a special base. So we're first going to use that power property, or product property, sorry. Then we're going to use the power property. And again, I do like writing log in cursive and natural log in cursive. That way they don't look like variables with coefficients or something like that. Like I don't like it looking like 10g, because I like to remember that log is all together. So let's reverse that. Let's go ahead and put them back together. So the big deal here is product and quotient properties don't work if there's coefficients. So you have to remove those coefficients first. So that means we're going to have to reverse that power property. So we've got to put the powers back up. We'll have log subscript 2 of c to the 5th power minus log subscript 2 of n to the 7th power. Now we can combine them into one logarithm by saying, hey, log base 2 of c to the 5th divided by n to the 7th. So the biggest issue I see students having is knowing when to write log multiple times versus when to write log a single time. Now you'll notice never ever ever did I write log times log, and never ever ever did I write log divided by log. So I've seen books go ahead and challenge people and say, hey, log base a of x equals 5, and log base a of y equals 8. Who knows what a is? Who knows what x is? Who knows what y is? We don't care. They might come up with this question though. Find log base a of x cubed divided by y. And you might be going, well, I don't know what x is. I don't know what a is. I don't know what y is. How can I do this problem? Well, we're first going to expand. Okay, we have a quotient, so we're going to use that quotient property. Log base a of the numerator minus log base a of the denominator. Then we're going to use that power property. Okay, now we're going to substitute 3 times minus log base a of x equaled 5. Log base a of y equaled 8. Well, that problem I can do to my head. 3 times 5 is 15, minus 8 is 7. So if you're taking an ACT or something and you come to one of those problems, that's probably one of them that's trying to help you discern whether or not you're getting bright flight. But you don't need a calculator. You don't care what A is. You don't care what X is. You don't care what Y is. You care what that comparison is. So just make sure you're applying your logarithm rules correctly, which is kind of the big idea behind this. However, there is a way to type these in your calculator, and that's the last rule that we have. I actually had one student call this the big baby rule. And I'll explain why this student called it the big baby rule. That was almost 20 years ago when the student called it that, so it's been a while. It's actually the formal name is change of base. On smaller scientific calculators, you only have common log and natural log. Okay, so typing in something like log base 3 of 20 or log base 8 of 2 is not the very easy thing. So we have the change of base rule, and there's multiple ways we could do it, but using basic keys, we would type log of 20 divided by log of 3. That's one way you could do it, using common log, or natural log of 20 divided by natural log of 3. That's the only time I'm going to do log divided by log, is when I'm doing change of base rule. So over here we'd have log of 2 divided by log of 8, or natural log of 2 divided by natural log of 8. And you might be wondering about, okay, what's this big baby thing then? Well, she noticed that this number was written in larger font. So log of your big font, and then your subscript is generally written in smaller font or baby font. So divided by log of your baby font, which is how they came up with big baby. If you have access to Desmos, you can actually type them in with the subscript. You just need to go into your functions menu, and you will scroll all the way down, and you will find it in, it's under the calculus menu, but that's where they have natural log, log, and log base. But you'll notice that all three of these have the same exact value. So that's why we can do either of the lower two to type the upper one into a basic scientific calculator, or maybe you're using your phone calculator or whatever. Just make sure you close your parentheses. Okay, so let's do the other one where we had 8 as the base and just 2 inside. We had 2 and 8, 2 and 8. Not 38, just 8. And we can see we're getting 1/3 on each of those. You might go, hey, why is that such a nice, we can make that a fraction. Well, let's think about that. Okay. Log base 8 of 2 is going to equal some exponent, right? So if I rewrite this, we'll have 8 to the x power equals 2. 8 is 2 cubed. And when I have double powers, I multiply. Oh, I need the x value so that my power becomes 1. So 3x has to equal 1. So that's why we're getting 1/3. So keep in mind that, yes, there are some similarities that we can see between these. I could have done that some other ways, but I felt like that was the least confusing. So keep in mind, change of base formula is to help you be able to type these into any calculator out there, not just the super fancy scientific ones. You do not have to have an expensive calculator to be able to calculate log decimal values. You can use the change of base rule, which is the log of the big font divided by log of the baby font. Now, when are you going to see logarithms? I see them in carbon 14 dating, but for some of you, you may not be doing something like that. But you probably, if you take physics or some upper level chemistry, you're probably at some point going to see one of these two formulas. It might be written like this, or it might be written like this. Okay, these mean the exact same thing. Why? Well, if I expand this, log of 1 minus log of h plus, remember 10 to some power is 1. Oh, that's 0. So we just have negative log of our hydrogen atoms. So pH is going to be your acidity. Your concentration of hydrogen atoms is usually in moles per liter. So let's say you have a pH of 3. How many moles per liter is that? Okay, well, we have to choose which formula we want to put it in. I'm going to choose the one on the right. Remember, they're the same thing. So substitute 3 for my pH. So I need to get rid of that negative sign. So I'm going to make this negative 3 equals log of H plus. Remember, my base is 10, so to solve for the hydrogen atoms, I need to put it back in exponential form. So 10 to the negative third is the number of hydrogen atoms we have, or 0.123. Okay, well, what if you had done the other formula? Okay, 3 equals log of 1 over H plus. It's ready to be reformatted, so 10 to the third equals 1 over the hydrogen atoms. Remember, 10 to the third is 1,000. To get rid of dividing by H plus, we multiply it to the other side. So 1,000 hydrogen atoms equals 1, then divide. 1 divided by 1,000 is 0.001. So both are going to work. It just depends on which format you want to be in. So keep that in mind. One other thing to keep in mind, I don't know if I said it, is that your base will always be greater than 0. It will not be a negative base. It will always be a positive base. So the rules that we had, just a quick refresher at the end, is we had the product rule, the quotient rule, the power rule, the change of base rule, you remember product was if you have a product, I'm writing it backwards this time, right? You can expand it. Remember, it goes both ways. If you have a quotient, you can expand it. And again, that goes both ways. If you have a power, that power can move out front as a multiplier. And remember, it goes both ways. And then change of base rule, log base A of B. And they do go both ways as well. Goes to log of B divided by log of A. And then a couple additional identities. Log of any base with 1 will always be 0. Any base to the 0 power is 1. And log base x of x, where these match, will always equal 1. If you know those rules, you are going to have so much power in your arsenal when it comes time to solve exponential equations or to work with logarithmic equations. And it's really going to help you out because the different ways that we can apply them and manipulate them allows us to solve. Maybe you're trying to find the half-life of carbon-14. Maybe you're trying to find how old something is based on carbon-14. Maybe you're trying to find out how long until a certain type of medicine will be under a safe level to be able to take additional medicine. There's lots of reasons to use this. pH values, earthquakes, magnitude of earthquakes, sound decibels, they all kind of relate to this. So having these skills can help us solve.
Thanks for learning with me here on Math with Michelle. If this helped, give it a like and don't forget to subscribe for more clear and simple math lessons. Got a question or topic you want me to cover? Then drop it in the comments. Until next time, keep practicing, stay curious, and remember, you've got this.